Uh, Hello, everyone. Let's wait for a couple of minutes. So I guess we can start our lecture. Do you hear me well? I see that.
Yes.
Okay. So let's start. Um, 6. So today we're going to discuss some stuff related to photonic crystals, some Bragg mirrors, some examples, band gaps, and some properties in these systems. So, photonic crystals. Maybe some of you already know something about photonic crystals, but anyway, I will explain it from the beginning. Suppose, for example, you have such permittivity. AX, Y plus AY, Z plus AZ. This is epsilon X, Y, Z. So the permittivity now somehow changes with the geometry parameters. So here's A is the period of the structure. Period. So basically, it can be changed in any direction you see in X, Y, and Z, but yes, this is periodic permittivity. So here's the question. What will happen with the dispersion relation in such systems? So to study it, we first will consider the most simplest case of 1D photonic crystal. So in such case, we can rewrite the permittivity like X, Y, Z plus D. So D is the same. Well, actually, I will write it here, just not to confuse. Here's X, Y, Z. The system, we can describe it like some layers, periodic layers, with D1, epsilon 1, D2, epsilon 2, and so on. D1, D2, and so on. It can be infinite, it can be finite, but here we say that D1 plus D2 is equal to D. It's a period of the structure. So to study such periodic systems, we must use the Bloch theorem. Most of you should know already something about Bloch theorem, but I will just remind you. Bloch theorem. This is very important in such systems. So to understand the Bloch theorem, well, of course, some of you remember that it is somehow related to periodicity, Bloch vectors, and so on. But we will start from considering the Schrödinger equation. So 2m psi plus u some potential and e psi. And this potential, we can write it like x plus d is equal to ux. So we have such system. And actually the Bloch theorem says that solution of such problem can be written in such a form. Psi x equal to e I k x phi k, where phi is some periodic function. So plus d equal to phi k x. But yes, actually that's all. This is the Bloch theorem. But I think it is useful to demonstrate it. Let's consider the same equation like this, plus ux psi e psi. Here we can substitute such relations x prime plus d. So the derivative over x is equal to derivative over x prime. Let's substitute it. So d over dx. Here, let me here. Right. Prime squared some function of x prime plus u x prime, also such function, e f x prime. So here's all the coefficients are the same in this equation. Well, it basically means that we can consider it like this. So you see that these coefficients are the same. Also, the function is the same. So we can rewrite it as f at x prime. And in this case, a is some function of phi. This happens because, well, this a, in order to work, this a should be finite. This is basically leads to our function. Thanks. I'm sorry, d. E I kd and fx. Yes, this is basically the Bloch theorem. So tell us about the solution of such periodic problem with periodic functions and so on. But in order to consider these layered structures and to solve problems with layer structures, to find some solutions, it is convenient to consider the transfer matrix method. So transfer method. First of all, let's consider the same periodic structure. So D1, D2, so D1, D2, and so on. We basically we remember that our electrodynamics equations are linear. So we can easily find the equation at D1 boundary. So here's the 0. Let's write the axis. So here's z-axis, x-axis, for example, y-axis. well, we put here 0, and we easily can find the equation at D1 through the solutions at 0 point. But it is only possible for components that are continuous on the boundaries. Then, first of all, let's consider the TM waves traveling in such systems, and we can write such solution, such matrix equations. So Ex, remember that we have which components we have in TE and TM waves. Some function T that also depend on that, and Ex at 0. Sorry. Hy at 0. So it basically means that some matrix help us to find the fields on some coordinate z through the fields at the beginning of the coordinates. For example, we will consider at that z equal to d1 plus d2. For the first layer, d1 will be the matrix t1, for the second t2, and so on, t1, t2, and so on. So let's consider this scenario. What can we write? We can write Ex d Hy d is equal to t2 t1, and also the fields at the beginning at 0. Oh, and from the other hand, we also can continue this equation because we know that we have a Bloch theorem. We can write it like this. Ex at 0, Hy at 0. Since we have Bloch theorem, so I write it here. Well, that's great because now we immediately can obtain the dispersion equation. How? It is quite easy because unitary matrix equal to 0. So this is our dispersion relation. Let's solve it. So first of all, we should write find the fields, electric and magnetic fields. So let's write the electric field. We also remember that in such systems, we have two waves that travel in plus z direction and minus z direction. So mathematically, we can describe it like this. So plus will be the plus direction, I keep z, so plus a minus I minus kz. And the same equation for magnetic field, Hy B plus E ZZ plus N P minus KZ. Well, rigorously here we should also write the exponent for with kx and x, but since we don't have any periodicity in x direction, we can neglect it for now. So we have to find these coefficients. In order to do it, we also remember the Maxwell equations. H equal to minus I omega epsilon over C. Also can rewrite it. I K vector product H equal to minus I omega epsilon of C, and here we for now we are interested only in x component of the electric field, so let's write x as minus C over omega epsilon, and this vector product results in minus kz hy, or we can rewrite it further. So kz ckz omega epsilon hy. So this is for actually this is for the plane wave traveling in plus, I will write it for plane wave in plus z direction, but also we have a wave in minus z direction. So for it, this part will be equal to minus ckz over omega epsilon and hy. Perfect. Now we are ready to write the coefficients. So in this case, a plus is equal to ckz omega epsilon b plus, and a minus ckz omega epsilon omega b minus. We obtain such system, and we are ready to find the magnetic field. So this results in hy c. So we basically have to substitute it here and obtain epsilon omega ckz A plus I K Z Z. Here's the minus A minus minus I K Z Z. For simplicity, let's call it for some coefficient alpha in power minus 1. So in this case, the initial fields E x it's 0. Obviously, it is A plus A minus, and magnetic field Hy at 0 is alpha minus 1 A plus minus A minus. Perfect. Yes, and from this equation, let's find the A plus and A minus. Now, so we needed to find the T matrix, the transfer matrix. So A plus EX 0 plus alpha HY 0 over 2 and A minus EX 0 minus alpha HY 0 also over 2. So we finally can find the how the T matrix looks like. So the fields EX at D1 boundary. Let's write it. So it's EX 0 plus alpha HY 0 over 2 IKZ D1 plus the same EX 0 minus alpha over 2 E minus I K D1. Or we also can rewrite it using the sine and cosine function. So it is x 0 cosine k z d1 plus I alpha sine kz d1. This is electric field. For magnetic field, we can write almost the same equation.
You forgot.
Just substitute it here.
You forgot a magnetic field in previous line.
Magnetic field? Where?
Yes, because when you write x0, next term you have to add h0.
Where sinus?
Yes, where sinus.
Where sine is? Sine is. You mean
just upper just you write ex0 cosine plus e
Yes.
alpha sinus. You should also
Sine.
add here h. You just x
Yes,
plus-
of course.
Yes.
Of course. Yeah, let me rewrite it. Yeah. Which way? Yes, of course. But well, yes, thank you. You're right. So I will write the final expression for the magnetic field. I sine kz d1 plus alpha cosine kz d1, and here also the magnetic field that I forgot previously. Yes. Well, as you can see, we can write the T matrix for the first layer. Nothing else like cosine kz d1. Here's also cosine kz d1. Here's I sine kz d1, also alpha, and here's I over alpha sine kz d1. Here's the transfer matrix for the first layer. Obviously, for the second layer, we just should, by the way, we also have to write here kz1, 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 because kz contains the epsilon, so it's only for the first media. So in order to obtain the T2, like D2, we have just to change kz1 on kz2, also d1 on d2, and also alpha 1. But sorry, alpha 1, 2, alpha 2, because here alpha also contains the kz and epsilon. So we obtained some matrices which are called transfer matrices that help us to find the fields that propagate through some periodic layers. For example, if you have like a lot of periods, n periods, you have here T1 and T2. So just in order to find the whole matrix, whole transfer matrix through all structure, you just have to write it like this in power of n when you have n periods. So it is quite easy and understandable as far as I understand. If you have here if you have some questions, you just can ask. Well, if no questions, what can we notice here? The property the determinant of t is equal to 1. For at least in our case, it is true. So this is a very important property for now for us, and we should get back to our dispersion equation with determinant of t2 t1 minus exponent I k d and unitary matrix equal to 0. So once again, it's dispersion relation. It gives us information of the dependence of omega on k. So we should find it. It is very useful for description such systems. So let's find it. For simplicity, let's call it, we know that t is t1 multiplied, t2 multiplied by t1, and let's call it A, B, C, D matrix for now, just for calculations. So we can rewrite the determinant A minus I k d, B, C, D minus A I k d. Let's expand it. I hope everyone knows how to do it. IKD D minus I k d minus BC. We can expand it further. So here's, we are just open the brackets and obtain AD. Here's a minus BC. And the third part, just IKT and D plus D. And also E to I K D. We can simplify it, obviously. One can notice that this is the determinant of matrix T, which is equal to 1, as we discussed here. The second part is nothing else but trace of the matrix T. And here's just the exponent, also equal to 0. So we got rid of this part by 1. Let's just rewrite it. 1 minus E I K D. Sorry, not, I did it wrong. It's like this. E I K D trace of T plus e to I k d equal to 0. Let's divide by the exponent e minus d minus 2 raised t plus e I k d equal to 0. And again, one can notice that we can just simplify it with cosine function. So it's basically is cosine kd equal to trace of matrix T. So for now, it is our result.
It's 2 cosines.
Yes, you're right. I will write it. I will write it here. Yes. So to find the final equation, we just have to find the trace of the matrix. So let's do it. For simplicity, again, just to simplify the whole expressions, let's introduce phi1 kz1 d1 and also phi2 kz2 d2. Yes, everything correct. So I will just so you basically have to multiply these two matrices and find its trace. It is quite easy. I will just I just want to have it in my eyes. So with the matrix for the first layer, for the second layer, it's the same. So let's write the whole trace of T. It is cosine kz. I'm sorry, I forgot. Cosine phi1 cosine phi2 minus, also we have alpha 1 divided by alpha 2 sine phi 1 multiplied by sine phi 2 and alpha 2 alpha 1 sine phi 1 sine phi 2. And the last part is cosine phi 1 cosine phi 2. And just group sine and cosines, and let's just rewrite the final dispersion equation. Cosine k d equal to cosine phi 1 cosine by 2. Mhm. Minus 1 over 2 alpha 1 alpha 2 plus alpha 2 alpha 1 multiplied by sine phi 1 sine phi 2. So this is our final dispersion relation, which give us information about omega and k. So once again here I will just remind that phi I is equal to kz di, and alpha I is just ckzi divided by omega, omega epsilon, also I. Yes, this is our dispersion relations for photonic crystals. So one also can notice that we can have some dependence on angle of incidence in our structure. So in order to just to find it, we can substitute kz. And we can rewrite the our alphas just with cosine theta I divided by epsilon I. As you remember that we did it with something like this with Fresnel coefficients and waveguides. So here, basically, this expression leads to the fact that we have some dependence on angle of incidence. So it actually, our system works like a uniaxial crystal. We can further transform it, this expression. For example, the first term, we can rewrite it with sum of cosines, cosine plus phi 2 plus cosine phi 1 minus phi 2 divided by 2, and also the second term. Also the same, almost the same. Cosine is plus divided by 2, and the part with alpha here. Oh, we can rewrite it like this. So basically we can leave it. Well, let's leave it now and just rewrite the whole expression. Cosine kd equal to 1 plus alpha. We just say that this part is just alpha for simplicity and analysis. Cosine phi 1 plus P2 plus also 1 minus alpha over 2 cosine with minuses. Sorry. Yes. So basically, why we did it? It is quite important because we can, for example, let's plot it. Let's plot this expression. For example, we can plot the left and right hand side separately. Here's the omega, and we want to just to plot the left and right hand side. So we know that left hand side is just a cosine. So it has two limits, +1 and -1. So it is some cosine function which have limits from 1 to -1. And the expression from in right hand side, you also can notice that basically it can be greater than 1 and with some parameters. So it's just some periodic function. It doesn't matter now actually. But here you see these regions. These regions where we have no solutions, real solutions in such systems. So basically it is a band gap. Here comes the band gap, like mathematically. You remember, maybe some of, do you know what is band gap in photonic crystals? Maybe someone can explain it. Guys? Okay, so basically you have some periodic structure and you shine light on it. For example, with this frequency, omega double prime. And since you have no solutions, real solutions here, you will just have evanescent waves. So basically, the light will reflect from this structure, and you will not achieve any transmission in your system. You will just have the reflection. So it is called the band gap in photonic crystals. If you will try to plot the reflectivity or reflectance spectra in such in such systems, for example, the Bragg mirrors that I will mention further today. If we will just plot the reflectance spectra, you will have here also, I will write 1 for simplicity. You will have something like this. So when your frequency is in a band gap of photonic crystal, you will have the zero transmission, and almost all the light will reflect from your photonic crystal. But it is this picture actually is for infinite photonic crystal. For finite structures, you will have some oscillations, some Fabry-Perot resonances. If we just plot the same, I'm terrible in drawing, but you'll just have something like this. Okay. Do you have some questions? Everything clear?
We have Fabry-Perot oscillations when all photonic crystal is finite, yes?
Yes. When you will just calculate or fabricate some systems, some photonic crystals. In real world, they are finite structures. So if the structure is finite, you will actually see on the spectra these resonances that related with Fabry-Perot. Yeah.
It's because of some kind of reflected rays from the
Yes.
Yes.
Yeah, it's basically it is related to constructive and destructive interference in layers.
Yes, it's because some of the rays are transmitted and they're reflected from the inner parts and interference to each other. Okay.
Yeah, that's true. Yes, that's right. So for now, I want to make a break for, let's say, 15 minutes or maybe 10 minutes. Let's make 10 minutes break, guys. So let's continue. Okay. So we derived the dispersion equation. Let's try to analyze it somehow. First of all, I should say that it is actually impossible to solve it to solve this equation analytically for arbitrary parameters. So it's analytically solvable only for some of them, for some specific parameters. But you always can solve it numerically. As far as I understand, you will do it on practices. Yes, let's. But for now, today, let's start from considering the normal incidence. As you understand, I hope normal incidence is where kx equal to 0. Normal. I will just normal. Let's see. Also, I will remind you about the kz. So you also should remember that kz is a square root of omega squared over c squared epsilon minus kx squared. Yes. And what is important for when we analyze the band gaps and photonic crystals, especially band gaps, it is important to know where the band gap is, so the positions of band gaps. So we actually see that it is somewhere here. But how to find it? Just the new expressions. So we just take our dispersion equation in this point. We know that left-hand side here is -1, or when you will find, when you want to find it here, it's +1. So in order to find the positions, you just need to take the derivative, and you will obtain sine v1 plus v2 plus 1 minus alpha over 2 sine v1 minus v2 equal to 0. So this this expression will give you information about the positions of band gaps in your system. Well, it's also for simplicity, let me redraw it. Omega. So there's -1, 1. we have the same periodic structure. To analyze it, we just also have to find the widths of the band gaps. We found the positions, but we're also interested in widths of band gaps. So here are several interesting points. For example, this one, where the band gap starts. Let's call it omega 0. And also this point where the
Sorry,
omega,
can
yeah.
you repeat, please, why we have sinuses there?
Sinuses. Well, you see, we have our dispersion relation. So we know that band gap somewhere here. We want to find the positions of band gap. So the exact frequency at which band gap is the center of band gap. And in order to find it, we just have to take the derivative of this function of our dispersion relation. So the left-hand side is 0, obviously, because here it's just -1. And the cosines become sines when you take the derivative. So here the sines comes from.
Why we don't have some added coefficients?
Well, basically, yes, you will have them, but now we are not interested in them. It's just the main point how to find them, how to find the exact position. So, the center of that. Yes, but now we want to plot the dispersion relation, how we did it with waveguides. It's also possible to do it with photonic crystals. We just it is just for asymptotics, and just to see how functions behave with some specific parameters. Yeah, also I said at the beginning, after the break, so it is almost impossible to solve it analytically, because yes, you will have some coefficients that you will not be able to find analytically. Therefore, we just trying to understand what happens qualitatively, not quantitatively, but just qualitatively. Yes. Yeah. Let's analyze it further. First point, for example, omega tends to 0. Obviously, cosine kt is equal to 1. Yeah, also from the Bloch theorem now, you remember that it was something like e I k x a function of yeah, is we have some periodicity here. So from this block theorem, we know that all our independent solutions lays in the region minus pi over d to pi over d, which is actually called the Brillouin zone. I'm sure that you heard some words about this. Yeah. Now let's expand the right-hand side of this equation of our dispersion equation. Let me just to take it with me. Yes. Yeah. Let's expand the right-hand side and left-hand side of our dispersion relation in the vicinity of k tilde goes to 0. So let's do it. We'll have 1 plus kd squared over 2 equal to 1 plus alpha over 2. It's the same. 1 plus phi1 plus p2 squared over 2. Yeah, plus the second one. Not cosine, sorry. One plus one minus two. Now we also can simplify it like this, and rewrite k tilde d squared 1 plus alpha over 2 1 plus 2 squared plus 1 minus alpha over 2 1 minus 2 squared. So why we did it? Because we can start to plot the no, I'm sorry, I will do it here. We can start to plot our dispersion. So k tilde omega here, as you remember, pi over d. Here's minus pi over d. Here's 0. So we also remember that we said that in our case for now kx equal to 0. We have the normal incidence. So then our phi1, for example, is just proportional to omega. And we can actually rewrite it. So I'm sorry. I will just rewrite it with you. Squared plus alpha y2 phi1. I hope, yes, everything okay. One plus 2 squared plus one minus 2. And it is proportional to some constant and omega squared because of our phi and normal incidence. So we see that we have some linear dependence of omega on k when k is near to 0. So we can plot it like this. So we have some linear dependence. So basically, it looks like simple. We have simple dielectric, and our system responds like simple dielectric. But what's next? We can analyze the band gap. So when we are close to omega 0, close to omega 0. Well, it means that our k kd in sine must be somewhere like pi, in the vicinity of pi. Therefore, we can write that it is pi plus some delta k and d. And we can substitute it into our dispersion equation. So let's do it. Cosine kd equal to 1 plus alpha over 2. Well, I will not rewrite it. I did it too many times. I guess all of you remember these equations. So we can just say that when you substitute it, you will obtain the cosine kd. We will have the -1 and 1 minus delta k squared is squared over 2. This is our left hand side. So the right hand side, -1 plus delta k right left-hand side, and here -1 plus some coefficient beta. So actually it should be minus. Should be minus because now here we analyze this point and we have the negative slope here. Therefore we should put here minus. So it's just some coefficient and omega minus omega 0. This is just some constant that actually we are not interested for now, because we just want to find some asymptotics. And so our omega in this case, something like minus omega 0 minus delta k squared d squared over 2 beta. And how it looks like? I will just put the marker here and the blue marker here. We see that we have one second. See that we have something like this. Something like this, and zero derivative in this point. Zero. Well, from quantum mechanics or particle physics, maybe some of you know such conditions. Well, it looks like near the band gap, it looks like the photon behave like a particle with negative mass in this point, but in the other point, for example, we studied this point, but maybe someone want to study this point. We will have the positive slope. So here we will have plus beta, and it will mean that it behave like a particle with positive mass. So from this we can write the band gap condition. So band gap well, obviously it is d omega over dk equal to 0. This is the band gap condition. I also forgot to draw it here. This is the first band. The second band may look something like here, like this, and also the next band, and so on.
It's like optical and with waves in solid state. Optical and
well,
acoustical.
I'm not so familiar with acoustics and such stuff, but
No, I mean in solid state when we describe the
you
perturbation.
mean phonons?
Yes, they called as optical and acoustical in phonons.
Yes, it's they look
Optical is higher and acoustical is lower.
yeah, you mean the dispersion of phonons?
Yes.
Yes, it looks similar, yes, but now we are talking about other stuff. We don't talk about phonons for now, but yes, it follows the same manner, and looks the dispersion is similar, yes. Obviously, it's just the schematic that we draw here. It's just the asymptotics. Real structures may look differently. So here, you see here is band gap. So it's just typical dispersion curves of photonic crystals. So just I hope you will remember it. Also important to note that these branches actually they can cross in some materials, for example, in graphene. So when you know the structure, the electric constants, you can build the photonic crystals. You will analyze it. You plot the dispersion band diagrams and dispersion diagrams, find the band gaps, the first, the second band gap, and so on. So it's also periodic. For example, here, just schematically, it is the second band gap, and so on. But now let's analyze the same equation with our dispersion equation that we took the derivative. Someone asked about the signs. This equation. Sine P1 minus P2 equal to 0. Let's a bit analyze it because it leads to some interesting cases. So first of all, let's say that phi1 plus phi2 is, we know that it is omega over c square root of epsilon 1 t1 plus omega over c square root of epsilon 2 d2. And also we know, we can say that it is equal to pm, where m is even integer number, not even, just integer number. The same for phi1 minus phi2. The same expression, say, I will just say that it is equal to pq. For the simplest case that we can analyze, for example, let's say that q is equal to 0 and 1, or m is equal to 1. We also remember that square root of epsilon is just the refractive index of our structure. This leads us to this expression. So 2 d2. I also can further analyze it. Omega over c to epsilon 1, just substituted, d1 is equal to pi. We also know that omega over c is our k wave vector, and also we can write it as 2 pi over lambda. And in the end, we will obtain the square root of epsilon 1 d1 is equal to lambda over 4. So let's try to understand what happens here. So we have the wave that travels to our periodic structure here. So the same d1 epsilon 1, d2 epsilon 2. So at this point we have several waves actually that travel into the plus z direction. It's like lambda over 2 traveling in right direction, and lambda over 2 traveling in opposite direction. Well, it means that in this point, we have constructive interference. It basically means that we have a mirror. So solutions of our systems are purely imaginary. There is no wave in our photonic crystal. Therefore, we have no transmission. And also, interesting real case is Bragg mirrors. Maybe you know, they are widely used in different setups, different research. It's just a periodic photonic crystal with several layers, also d1 epsilon 1, d2 epsilon 2. So we usually n layers. We have some incident wave, we have reflected wave, it's also transmitted wave. This is our period D. So as we already know, just to analyze and to find such Bragg mirrors, so we just can use already known the T matrix method, and just to find the transmission coefficients. So it's just possible to write it like from the right side. We have some matrix that relates the fields from the left side. It's just reflections, incident plus reflected, and just incident field, and the transmitted field on the right part. And in this case, as I already mentioned, that M is just a matrix multiplication of transfer matrices of different layers. So in this case, you also can find, you also should know that your K tilde should obey the dispersion equation when it's real. When it's real, we have the standard plane wave solution like we did several times in waveguides and so on. But when omega, our frequency is in the band gap, we have k tilde is imaginary, so we have only evanescent waves. That's why the frequencies that lay in band gap just reflects our frequencies or wavelengths as you wish. So the last part that I want to discuss today is effective medium approximation. Also an important case. For example, for very small structure. When I say small, I mean that the wavelength of illumination is much greater than the period of the structure. So in this case, photon cannot fill small structures because in one wavelength you can have several periods of your photonic crystal, and in this case photon will not fill at all, and we will just have some effective medium. So what are the parameters in this case? So let's write it. KZ1 D1 is much greater than 1. Also KZ2 D2 is much less than 1. And K tilde D is also much less than 1. Again, we can rewrite our dispersion relation because this is the small parameters. We again can replace the cosines function, cosines and sines functions. So let's do it. 1 minus kt squared over 2, left hand side, and the right hand side 1 minus phi1 squared over 2, 1 minus phi2 squared over 2, minus this 1 over 2, and we can a little bit expand the alpha functions that we had in brackets, like where these are alphas. We can expand it in such way: D1, D2, epsilon 2, epsilon 1, and V1, V2, plus epsilon 1, epsilon 2, V2, V1, and here also V1 and V2. What's next? Let's just expand it. 1 plus yes. 1 plus k tilde t squared over 2 equal to 1. No, and now it's minus 1 squared over 2 plus p2 squared over 2 no, it's also minus, should be minus and bracket also 1 over 2 epsilon 2 or epsilon 1 d2 d1 p1 squared plus epsilon 1 epsilon 2 d1 d2 and v2 squared. And we can just delete this, also this, and something like this. What we'll have k tilde d squared equal, just let's collect the parts with phi1 and phi2. Epsilon 1 d1 plus epsilon 2 d2 over 2 plus v2 the same epsilon d1 plus epsilon 2 d2. No. I almost forgot. Here epsilon 1, epsilon 2. Here also epsilon 1, epsilon 2. And we can just move this part just here. What we'll obtain? We will obtain kt epsilon d1 plus epsilon 2 d2. Now let's expand the phi functions. So it's omega squared c squared d1 plus d2 minus kx squared d1 or epsilon 1 plus d2 over epsilon 2. And well, we can further rewrite it because this is d, our period. So omega squared c squared t minus kx squared and the same the same part, epsilon 1, epsilon 2. Now we can finally just write a very familiar result. K squared divided by epsilon 1 d1 plus epsilon 2 d2 over d plus kx and the same bracket. D2 over D. No, not the same bracket. No, sorry, it's my fault. It's just epsilon 1, epsilon 2D. It's the opposite. It's D1 plus epsilon 2 D2. Yes, now it's right. So does someone know what is this expression?
It's a dispersion rule, but we can find here some kind of permittivities as perpendicular and parallel, like in the terms of denominator, we can rewrite it as y quadrant squared equals to k tilde squared divided by epsilon parallel plus kx squared divided by epsilon perpendicular.
Yeah, it's right, but it is dispersion relation, but dispersion relation of what? Of which system? I'm sure you know this system.
In general,
and you,
our system in general.
yes, in general. Oh, well, okay. It is just dispersion of uniaxial crystals. So I'm sure that you did it in bachelor. You just maybe forgot. So our photonic crystal, that one-dimensional photonic crystal, is nothing else, just uniaxial crystal that is convenient and studied a lot. This is actually all that I wanted to talk about today. If you have any questions, just ask.
Yes, sorry, I have a question about that equation with sines that we use to find the band gaps. So I don't quite understand how we got that equation from the dispersion equation with cosines. So with respect to which variable we take the derivative there?
So you see, here you have our dispersion that we obtained. This one. We just want to somehow asymptotically, not rigorously, just asymptotically analyze it. Also know that important features of such photonic crystals is band gaps, its position and width. And in order to find the position of band gap, we know that it is somewhere here, here, at this point. So just to analyze it, we just take the derivative of this expression. we also know that
Derivative by k?
yes, sure. Just to find asymptotics. Nothing rigorous and nothing like exact. Just to look how functions behave. You know that when you take a derivative of a cosine, you will have a sine. So that's all. That's all the trick.
Okay, my question is that we have 3 different wave vectors, k1, k2, k tilde, and what derivative by what wave vector?
So we have kx equal to 0. K1 or ky we also don't have ky because our system is like this. So we have only kz here. And we just take the derivative over k tilde because you see here well actually it doesn't matter. You see we can take derivative of by by omega. Here it's really doesn't matter.
But we have different permittivities, epsilon 1, epsilon 2, and different d in these phases, phi 1 and phi 2. So it's not just that simple, I think.
Yes, you have different permittivities, phi 1 and phi 2. But they will not really affect the they will not really affect qualitatively, you know. It's just yes, it's not exact, but just qualitatively like describe what just happens. Yes, absolutely, you're right. It's not so easy, but just to take a look on something, just quick analysis, it make work. So, more questions? If no more questions, then I guess for today that's all. I also we don't have English speaking guys. Я тогда перейду на русский. Я хотел спросить, вам прислали на прошлом занятии домашку?
Да, мы сделали к этому занятию.
То есть к этому занятию вы сделали домашку?
Мы сделали последнее домашнее задание, получается, по векторным гармоникам.
Ага, хорошо. Тогда я думаю, что я дам какое-то не очень большое домашнее задание после следующей лекции.
А сколько у нас еще домашних заданий осталось?
Не больше 2.
То есть следующее и еще одно?
Следующее еще одна, я думаю, да.
Все, понятно, спасибо. У нас остались только фотонные кристаллы, получается, да?
Фотонные кристаллы, S-матрицы, ну и вот все вот это вот. Я не уверен, что я что-то еще другое расскажу про фотонные кристаллы, но расскажу про S-матрицы. С T-матрицами мы сегодня как-то познакомились, вот познакомимся с S-матрицей.
Понятно, спасибо большое.
А, Тогда, если ни у кого больше нет никаких вопросов, совсем никаких, тогда, наверное, я заканчиваю.
До свидания.
А можно вопрос? Следующие лекции тоже будут онлайн или в оффлайн формате?
К сожалению, все лекции наверное, до конца будут онлайн. Я возвращаюсь 24 декабря, и 24 декабря это тоже вторник. И я думаю, что это же, скорее всего, будет последнее какое-то занятие официальное. 31 декабря вряд ли кто-то захочет приходить. Ну, я точно. Я думаю, что 24 декабря мы сможем устроить, как на мидтерме, исправление домашних работ, кому нужно. Вот это можно будет сделать очно.
А у нас 24 декабря вроде защита НИР.
Да, это правда. Я думаю, что защитный мир будет после пары.
Можно их все-таки не делать в один день, пожалуйста. Обычно защита НИР — это длительное мероприятие, которое занимает весь день.
Я знаю, что оно занимает весь день. Я посмотрю, что можно сделать с этим. Если что, я могу попросить Дашу передвинуть защиту НИР на какой-то
Если у
другой.
нас дистанционно, например, будет защита домашек, как на мидтерме, то можно провести в любой день, кроме 24-го. Просто выбрать, когда всем удобно. Например, там в субботу или в пятницу, когда у кого нет пар, например.
Давайте я обсужу это еще с Ильей и Олей, и мы посмотрим, либо это сделать как-то не на занятии, либо это... Да. Выбрать какой-то день, короче, другой. Либо попросить Дашу Замотину перенести защиту НИР на какой-то другой день.
Мне кажется, проще было бы перенести именно мидтерм, потому что его проще провести в другое время. Если как в этот раз сделать дистанционно.
Наверное, да.
То есть просто, по сути, надо узнать, у кого когда время будет свободно и кому удобно, и провести.
Нет.
Потому что не все же будут его писать все равно.
Просто, как сказать, довольно-таки просто проводить вот такую вот защиту НИР, защиту задач во время, отведенное вот именно под наш предмет. Потому что время уже зарезервировано, и все как будто бы должны приходить. А так надо будет спрашивать, кому как удобно с этим. Ну ладно, короче, это...
Ну,
что-нибудь
ладно.
придумаем.
Да. Спасибо.
Спасибо, до свидания.
До свидания.
Всем пока. Если больше ни у кого вопросов никаких нет, то, наверное, все.